This is Core Pure 2 from 2023. Let's just go ahead and get straight into it. To do the integral of a polar thing, you need to do half the integral of r squared between the two limits, in this case pi and 0, which is the initial line. R squared, we'll just square this, gets you 4 into this thing here. And then you can integrate sine and cosh, sine and cosh both integrate to each other with no pluses and minuses, so it's super nice. I can use this 4 to make this half into a 2. Put in pi and 0. Now, you just need to now know that what sine and cosh are. Cosh is this and sine is this. So now you can put the values in. When you use the zeros, each of the 0 is 1. So you get 1 plus 1 over 2 in this case, which is 1, and then 1 minus 1 over 2, which is 0 for the other one. And now there's some cancelling here and some nice going together of things, just to leave you with 2e to the pi and then just minus the 2 at the end. You can also, just from the very start, to make the entire question much easier for yourself, sine plus cosh is by definition just e to the theta, which then you could say is e to the half theta, and then you have a very easy job integrating and a very easy job putting the numbers in. So yeah, that would also be a nice little trick you can use there. Question 2 is just a garbage question. E to the x is this by definition. I think it's in the formula book actually, but whatever. So 1 mark for that. And then you have to do this. And like, there doesn't seem to be a nice way of doing this. However you do it, it's just garbage. So what I did was I just replaced x in this formula here with e to the x minus 1. That seemed like a sensible thing to do. But then, of course, you need to expand out these guys up here. So I did that. This one and this one cancel, which is at least quite nice. Ignoring every term beyond this because we're assuming that this stuff gets just too small, I guess. And now we just need to make the substitution again for all of these e to the x's. I'll first collapse some of it together. The e to the 2x's square, which is, sorry, cancel out, which is kind of okay. The other stuff doesn't. But now I just need to put this into each of these things again. This one being e to the x cubed, of course. So I need to cube all this. Like, I'll be done once I do this, but it is just quite annoying. And I only need to do it up to the x cubed term, I guess. So I can ignore any terms after all of these. But cubing this is quite annoying, at least. I just decided to do one copy of it first, and then this is this thing squared up to x cubed. And I did this in my head. I just said 1 times 1 is 1. To get x's is either x times 1 or 1 times x. That's going to be 2 of them. To get x squared, it's either x squared times 1 or 1 times x squared over 2, of course, both of them. That gives you a single x squared. Or you get the x times the x to give you another x squared, which gives you 2x squared in total. And then likewise to the x cubed. It's either this times 1 or 1 times that, and then these 2 times together, and then there's 2 copies of that because you can either do this times x or x times that. You eventually get this, and then finally you expand those out. I've ignored everything else, by the way. I'm just looking at this cubic thing right now. You finally get this, which you can then replace this cubic thing with, and then you can just expand out everything finally and collect everything together, hopefully in a calculator, and get the answer up to x cubed. Just a dumb question. I'm not going to lie. I don't really understand the point of it, aside from just asking you to do a ton of just not fun maths or whatever. M squared is this thing times itself, of course, so it's that times that plus that times that first, so that's minus 4 plus 30 is 26, sorry, is 34, because it's plus 4, of course, minus 2 times minus 2, plus 30, and then minus 2 times 5 plus 5k, and then minus 2 times 6 plus 6k, and then 30 plus k squared to finish. Add 11m. 11m is just what happens when you times every input by 11. And if we add these two things together, so we just add each individual input together, we'll get this. But that's apparently some multiple of the identity matrix, so that must be A00A. But that means, of course, that 12 is A, obviously, and it also means that this thing must be 0, which gives us k as minus 9. Likewise, the same thing if you tried that bit there. So, okay, determine invariant lines. Now, this is a very classic technique that has seemed to have come a couple of times. We do m times some point xy, except on a line, y is mx plus c. So what we can say is it's going to be m times x, mx plus c, because this is doing the matrix times some coordinate that's on the line, because it's x, y, but y is just mx plus c. And that gets you not to the same place, not to x, mx plus c, but to some other place on the line. So x is some other x coordinate, big X, and some other y coordinate on that same line, m big X plus c. So now we can do minus 2 times x plus this equals big X, just reading the top row bits, and the bottom row bits read this. And now these things have to always be true, because this, for an invariant line, it means wherever you try to apply this matrix to on the line, it always goes somewhere else on the line. So this must always be true regardless of the x position to start with, as long as it's on your invariant line. So these are identities, which means that we can first substitute this x into here. This big X from this goes into there. So that gets you this. You can expand out. But because this is always true, that means that the variable parts of it, which is the x's, must just be the same. They must all cancel out, or they must just have the same thing on the left as the right, because it's always true regardless of the x's. So 6 minus 9m over here must always be equal to minus 2m plus 5m squared over there. And likewise, the non-x's, the minus 9c, must always be equal to the non-x's over there, because this thing is always true, because you're on a line that has this rule that always applies to it. This we can actually solve pretty quickly. If we just notice that c is 0 is a solution for any m, then that's great. And if c isn't 0, then as long as we use m as minus 2, c can then be any value. So for the second condition about having the constants be the same, we can either have c as 0 for any m value, or m as minus 2 for any c value. But remember, we also need this condition to be true, that the x's need to match. That gives us a quadratic, which has these two solutions. Now notice this one is the same, so that's cool. So m is minus 2 works for both, and you can have any c in that scenario. So an invariant line would be y equals minus 2x plus any value. That would be fine. Or you can have m is minus 0.6, in which case c would have to be 0, I think, because we're now in this case here. And for this one here to work, c would have to be 0. M equals 0.6 isn't going to make this work unless c is 0. So these are our two versions here. Which of these have fixed points? And now we can do the slightly different version of this, where we say, well, the matrix times xy must just be xy, right? That's a fixed point. Xy goes to itself, xy. So now we do the same thing. That's the top row, that's the bottom row, and we just need this to be true. And if you rearrange both these, they turn out to be the same thing. It's y equals 0.6x, which we saw before. So this is the line that is actually, it is an invariant line. It's an invariant line where every point on the line just goes to itself. Whereas this is an invariant line, or a case, or a set of invariant lines, where every point goes to somewhere else on each one of those lines. Maybe some of them go to themselves. I guess 0, 0 comes to mind, but not as a general rule. Question 4. So we have a polar curve here. Sketch it. So okay, we've got this is the initial line. The pole, the pole, is the origin. I actually learned that today, so that's fun. I've never bothered reading that word before, apparently. When theta is 0, you get, obviously, cos 0 is 1, so it's 3 plus root 5, so that's going to be the point on the initial line. And I think I just expected to know that this is one of those cardioid shapes. I think that's what it's called anyway. You can put in some more values if you want, like when cos is pi, you get minus 1, so it's 3 minus root 5, which is a positive value. So it's a positive distance from the origin. It's just in this direction because pi is in this direction as an angle. And then you can use pi over 2 and minus pi over 2 and get these. I think you're just supposed to know it looks a bit like this shape. Given it's only 2 marks, I think you're just supposed to have memorized that. The tangent to C at the point A is this, parallel to the initial line. So it's kind of like this parallel line here. Parallel to the initial line means dy by d theta equals 0, just something to know. Parallel to the vertical line is dx by d theta equals 0. So okay, y is equal to r cos theta, r sine theta, as it always is. We can't just differentiate that because r itself is a function of theta. So we put that function of theta in, and then we can differentiate it. Now, to differentiate this, I just said 3 sine theta differentiates to cos theta, and then I just did this with product rule. So sine differentiates to cos to make this a cos squared, and then leave the cos alone, of course, and then differentiate cos for minus sine, which makes this a minus sine squared. And now we can just set this equal to 0, and we can replace this with cos squared, 1 minus cos squared to make this, and this is just a function of cos. Use the quadratic formula, or just use a calculator. Or actually, you can also given this, you could have done a bit of factor theorem, which I thought is what I remembered doing, but apparently I didn't. I just used the formula. It's probably a more sensible thing to do. This value is negative. We know cos is positive in this range, so therefore this is the correct value, which is the one they wanted us to get. Hence, determine r, well, cos theta is 1 over root 5, so you stuff that in, and they cancel, and you get 3 plus 1, which is 4. And that will be our answer there, which is good to go. Excellent. Question 5. So we have 2 points or 2 vertices on a hexagon and their opposite vertices, so like here and here, which means the midpoint of the hexagon is just the center of the hexagon is just going to be the midpoint of the 2 ones you've been given. So just average the 2 x coordinates, average the 2 y coordinates, and you get what they wanted you to get. Given beta is this, show this thing here. So beta is that, put that in there. Z1, put that in there. Alpha, put that in there. Say the left-hand side equals, and then just do some very basic maths. Pull out 32 and do some multiplying, and you get the right-hand side is 1. Good. The vertices of H are given by this thing here. Write down the roots of w to the x equals 1. So the first root is obviously just 1, or e to the power 0. if you're doing this in this form. And then the second root is just e to the, well, okay, so 1 is equal to e to the 0, or e to the 2 pi I, or e to the 4 pi I, or minus 2 pi I. It doesn't really matter. You can go as far as you want. And then just essentially just sixth root all of those things. So just divide all these powers by 6, and you end up with all these. That's just how I would do it. It's up to you, though. Now, this last part, I believe the mark scheme gave at least a few different ways of doing this last part. And unless I'm mistaken, I somehow still managed to find a way that they hadn't given. I wasn't trying to. This was just the way that I thought to do it, even though it's really dumb. What I thought to do was just do it the normal way, which is you just take one of your vertices and you multiply it repetitively by one of the roots of unity in this case, and you just bounce around to all of the other roots. Unfortunately, that doesn't quite work here because this isn't centered at the origin. But that's okay, because what we can do is we can just move this 3 down, sorry, 3 right, left and 7 down. And we can then say that it is, and then at the end, we'll just move it back again. So I'm going to take this root here, which is, sorry, this value here, which is, you just type in cos pi over 3 sine pi over 3, get this. And I'm just going to type, because we're looking for them in Cartesian form, I'm just going to multiply this by this and get this. Again, a calculator can do this if you're a bit lazy. And then this isn't quite right because this isn't the moved hexagon, because I moved it, remember, to make it center 0 so that this tactic works. So let's just move it back. Let's just move it 3 right again and 7 up, because we moved it 3 left and 7 down originally. And we'll get this here. And likewise, to get the next point, we could times this by the next one, or we could just times Z2 by this. Because essentially, if we imagine that's Z1, timesing it by this gets it to there. And if this is Z2, the opposite one, then we'll get this one as well by timesing it by this. So let's do that, and then that gets you this. You move it back again to get you this answer here. So again, just shifted it 3 to the right and 7 up. And now, again, instead of, there's a bunch of ways you could get the last 2, I guess. You could take the 2 that you just found and times them by this, because that again will shift it 1 further again. Or you could take the starting 2 and times them by this instead, which is what I did. It really doesn't matter. Again, choose this one and times it, and then move it back again, and then choose the other one, which is this, shifted, and move back again. Sorry, I should have mentioned this one here comes from shifting this, obviously 3 left and 7 down, which is the same way that I shifted this one here. Okay, cool. So that is about that. Good question number 6 then. So given y is this thing here, now I got excited when I saw this question because I thought we were going to use some Leibniz differentiation, but we're totally not. It's just a proof by induction, which is exciting anyway, isn't it, right? Proof by induction, I guess. N equals 1. Just follow the formula, and you end up with this here. And if you just differentiate this, of course, when n is 1, this just means dy by dx. So when you differentiate this and use some product rule, you end up with the same thing. So it totally works for n equals 1. Then we assume it's true for n equals k. So this is our assumption line here. And then we just investigate what happens when n equals k plus 1. Now, by definition, d to the k plus 1 of y is d by dx of d to the ky dx to the k. And by the assumption step, this is this. So we'll say by assumption step there. And then we'll just differentiate it using some product rule. So it's this times all of this. So differentiate this first with 2e to the 2x, leave this alone, and then leave this alone and differentiate this. These are just numbers, right? So this just differentiates to cosh, as we saw before, and this to sinh, and we end up with this here. Let's continue. So we have this. I'm going to group this by sinh and coshes, which looks a bit like this. These twos cancel, which is nice of them. So we just end up with this. I'm going to regroup that back up, I guess. And actually, I think first I'm going to collect 3 to the k's and numbers, likewise here and here. Now group that over 2 again to get this. And now 3 times 3 to the k is just 3 to the k plus 1. And so by definition, this is totally what we want. And now we just need to write that normal spiel about how, if it's ever true for n equals k, it's true for n equals k plus 1. We've shown it's true for n equals 1. So therefore, it's true for all integer values with k. Just need to write that kind of thing over and over again. I just couldn't be bothered. We have a volume of revolution to do here. It's revoluting around the y-axis. I just made up a word there, but no one noticed. That's fine. So it's pi times the integral of x squared dy. Rearrange this for x squared, except I couldn't be bothered. I did it for 16x squared, and then I'm just going to divide this integral by 16 when I shove this whole result into there. So that's fine. This is the only bit of this that's tricky to integrate. I just did integration by parts. So integrate cos 5 over 2y to get 2/5 sine 5 over 2y, leave the y alone, and then take away the integral of this thing differentiated, and then they steal this thing integrated, and you end up with this, and then this thing integrates super easily to 4/25 cos 5 over 2y, and that minus will change to a plus, and that will be the entire thing that you need to put into there. These two are super easy to integrate. If you haven't seen this done by parts in the way that I just said out loud, then great, do it normally, I guess, but I just do it like that because it's much faster. These are obviously horrific numbers to put in, so you just type it all in to calculate it, and you get the answer very quick and easy. Given 100 berries were picked, well, this times 100 is 226, but it does specifically say that this was the largest one. So therefore, that's the upper bound of how much juice you could get. And the mark scheme's kind of interesting. It says if your answer is between 220 and 250, which it should be, you can conclude either way, apparently. So you can either say, so yeah, it seems reasonable that you could expect 200, or you could say, no, because that was the largest one, and you're not getting juice out of the flesh and the seeds, which are all whey stuff. It's likely that you're not going to get to 200. You could just say that, which is interesting. Good. Question number 8 then. So we have a cubic function, and the cubic function has roots that lie in the same line on the complex plane. Now, for that to happen, firstly, think about a cubic function. It could have 3 real roots. Now, if it has 3 real roots, that of course means that in the complex plane, its 3 roots lie on the same line, right? Because they're all on the real axis. So the line y equals 0 is totally a line they could lie on if the cubic has 3 roots. Now, if it only has 1 root, then that means that it's got 1 real root, which also lies on the real line, like x equals k, for instance. But it's also got 2 complex roots. Now, you could suggest that maybe the straight line here could be a vertical line or a diagonal line or whatever, but it actually can't be because the other 2 roots have to be complex, but they're of the form alpha plus minus beta, which means the real part of them is the same for both. So it can't be like a diagonal line like this, because then the real part would be different for both of them. It must be something above this value and something below it if they're in a straight line. So it must be k plus beta I, k minus beta I, if they're in a straight line, if you're in this case here. So you can just have any line of the form x equals k, where k is just some real number. And those would be the 2 solutions. I probably should have thought about what happens when you have a repeated root here, but I mean, fine, that just gives you 2 real roots, and they're in a straight line, y equals 0 again. That's fine, it's just one of them's repeated, so I guess don't need to mention that, we've already covered it. Okay, so we've got this precise cubic here then. It has 1 root here, so obviously it's got a root of 3 over 2 minus 3 over 2i. And it also, of course, if its roots lie on a straight line, that means we're in this red case where got a root here, got a root here, the other root must just be 3 over 2, the real number in between them. So okay, that's fine. We've got a different cubic here, got 3 roots, and its roots also lie in a straight line. And f of z and g of z have 1 root in common. Now, if g of z's roots lie on a straight line, it could just be the same line, except then all 3 roots would be in common, and they only have 1 in common. Now, it can't be a different vertical line, because then it would have no roots in common with the 3 reds here. So it must therefore be the horizontal line case, and the one that's in common is the real one. So therefore, the real root in common is 3 over 2, and g of z has 3 real roots, is what we can conclude from this simple sentence here. And it has another root at minus 4, which means, of course, we can find out the last root. The common root is 3 over 2 over z. The last one, well, the 3 of them must just multiply to make minus 12 over 1, using rules about, roots that we know. So alpha, therefore, is 2. And that's all good. And then it says, hence solve f of z equals g of z. Tons of ways you could finish this off. I chose to completely ignore these and just say f of z is just 8 lots of, because of the 8 here, z minus the 3 roots that we know f of z has that we saw earlier, and g of z is just, because there's a 1 here, we can just say it's the 3 roots like this. Just set them equal to each other. Of course, you can multiply out these 2 brackets as well, which gives you this. It's always easy to multiply out the 2 brackets that have conjugate roots here, because the roots always just behave nicely, so you can just do it on the calculator maybe if you're feeling lazy. Of course, you can divide by z minus 3 over 2, as long as you say z equals 3 over 2 is a solution to this equation, which they already told us because we know they had 1 root in common. But now you can get rid of it, you can expand this out, you can do some more expanding, and you can solve this, and you get the other 2 roots are that there. And we'll be done with question 8. Question 9 then. Always like these coupled ones because you just kind of have to mess around with some algebra until you get the answer. So I just differentiated this to give me this. X differentiates to dx by dt, of course, and y likewise. And then I just threw in the two results for dx by dt and ty by dt to get this. So that's just me throwing in those two lines into this line here. I think I expanded that all out and times by everything by 40,000 just because I was keeping my eye on the answer as I was going along. You can group that up to make this, I guess. And now you can say, well, what do you need to do with this x here? Well, you can just rearrange this equation for x. That gave me this. Again, I think I divided by 0.032 to make the x coefficient 1, and then just times it by 89.6 as you throw it in there. And then when you rearrange that, you get exactly what they wanted you to get. So that's nice. Determine a general solution then. So we've got a second order differential equation here. We'll ignore the 2560 and just make it equal to 0 first, and just solve the auxiliary, is it called an auxiliary quadratic equation, something like that? Just use a calculator. M is either of these two. Because they're both real and distinct, it's a really easy case. You just have y equals a e to the first root t plus b e to the second root t, so that's fine. Yeah, I'm just wondering, should I have had minuses there? No, it's fine, it's fine. Anyway, and then, sorry, I've lost my train of thought completely. Oh, and then we have to, of course, consider the 2560. Now that's just a constant number, so we'll just need to use something of the form y equals k or y equals lambda or whatever. But of course, when we differentiate that, we get 0. So we're just going to, when we substitute this into this equation here, we're just going to get 13 lambda equals 2560, which gives you lambda is 2560 over 13. And we can just add that on to our particular solution here, and we'll get the general solution there, which is good. And yeah, now we know that when t is 0, x and y are both 0. So we can throw that result in, and we get one part of a simultaneous equation. Now, how do we get the other part? Well, logically, dy by dx, or sorry, dy by dt is probably also going to be 0 at x equals t equals 0 because the whole thing hasn't started yet. But you can also verify that in your head because at t is 0, x and y are both 0. So therefore, this whole thing is 0. So dy by dt is 0. So anyway, let's differentiate this thing here, as we always have, or very often have to do in these questions. Just differentiate it, and then we can say dy by dt is also 0 at t is 0, which gives you this. And then you can actually just solve these two equations in a calculator if you just put that number over there maybe and just use the simultaneous equation function. And you get a is that and b is that. So then you write out the whole thing one more time, and you'll have your answer there. To be effective, the thing needs to reach this eventually. Well, the word eventually gives you a hint. You just need to send t to infinity. And if you do that, both of these terms become 0. And you get just y equals this, which is roughly 197, which is good. So as long as you're prepared to wait around all day, the treatment will be effective eventually. And yeah, thank you so much for watching. I'll see you next time.